Welcome, aspiring coders, to a fascinating exploration of programming languages. Today, we'll unravel the intricacies of the digital realm and understand the fundamental concepts that power our technological landscape. Web pages, mobile applications, and software solutions shape our daily experiences. These are created using programming languages, the building blocks of the digital era. A mobile application, commonly referred to as an app, is a software program designed to run on mobile devices such as smartphones and tablets. These applications leverage the unique features and capabilities of mobile platforms to provide users with a wide range of functionalities, services, and entertainment options. Dive into the behind-the-scenes magic of websites like Facebook, YouTube, and Twitter. Programming languages bring these platforms to life, enabling seamless interactions and dynamic content delivery. Understand the difference between front-end and back-end development. Front-end deals with user interfaces, while back-end manages server-side operations. Together, they create a cohesive digital experience. Understanding how computers read code is fundamental for programmers, as it allows them to write efficient and error-free instructions that can be seamlessly translated into machine-executable actions. The choice between compiled and interpreted languages depends on various factors, including the specific requirements of the application and the development process. Explore the fascinating process of how computers interpret code. Binary code, the language of machines, is translated into machine code through a series of complex operations. Computers, being intricate machines, follow a specific process to understand and execute the instructions written in a programming code. The journey from human-readable code to machine-executable actions involves several key steps. Writing code. Developers write code in high-level programming languages, such as Python, Java, or C++. These languages use syntax and structures that are closer to natural language, making it easier for programmers to convey instructions. Source code. The written code is referred to as source code. It is a set of human-readable instructions that convey the logic and functionality intended by the programmer. Compilation or interpretation. The source code needs to be translated into a format that the computer can understand and execute. This process occurs through either compilation or interpretation. Compilation. The entire source code is translated into machine code, binary, before execution. This results in the creation of an executable file. Interpretation. The code is read and executed line by an interpreter, without creating a separate executable file. Machine code. The translated code, often referred to as machine code or binary code, consists of low-level instructions that the computer's central processing unit, CPU, can directly execute. Execution. The CPU processes the machine code, following the sequence of instructions provided. Each instruction corresponds to a specific operation, such as arithmetic calculations, data storage, or conditional branching. Output. The execution of the code produces the desired output, which could be the result of a computation, the display of information, or any other programmed action. Error handling. If there are errors in the code, such as syntax errors or logical mistakes, the computer may encounter issues during the compilation or interpretation stage. Developers need to address these errors to ensure the code functions as intended. Binary is a numerical system used by computers to represent data and instructions using only two digits, 0 and 1. Unlike the decimal system we commonly use, which is based on 10 digits, 09, binary operates on a base 2 system. This means that every digit's value is a power of 2. In binary, each digit is called a bit, short for binary digit. A sequence of 8 bits forms a byte. The binary system is the fundamental language of computers, as it allows them to process and store information in a way that aligns with their electronic components. Bits and bytes. Bit, binary digit, the smallest unit in binary, representing either a 0 or a 1. Byte. A group of 8 bits. Bytes are often used as a basic unit of storage and data representation in computing. Machine code. Computers use binary code as machine code, the set of instructions executed by the Central Processing Unit, CPU. Machine code consists of binary instructions that the CPU can directly interpret and execute. Uncover the ASCII code, a standard encoding system for text characters in computers. Witness how letters and symbols are represented in binary, highlighting the bridge between human language and machine understanding. ASCII, which stands for American Standard Code for Information Interchange, is a character encoding standard used in computers and other devices to represent text and control characters. Here's an explanation of ASCII. Definition. Purpose. ASCII is a character encoding scheme that assigns numeric values to letters, digits, punctuation marks, and other characters commonly used in computer systems and communication. Character representation. Numeric values. Each character in ASCII is represented by a unique numeric value ranging from 0 to 127. Standard. ASCII originally defined 128 characters, including 33 control codes for devices such as printers and teletypes. Character set. Alphanumeric characters. ASCII includes representations for uppercase and lowercase letters, a Z, numerals, 09, and various punctuation marks. Control characters. ASCII also includes control characters, such as newline, tab, and carriage return, which have specific functions in text formatting. Binary representation. Bit size. ASCII characters are encoded using 7 bits, allowing for 128 unique combinations, 2 to the power of 7. Binary values. Each ASCII character is represented by a unique 7-bit binary number, making it compatible with early computer systems. Extended ASCII. Expansion. Over time, an extended version of ASCII was developed, allowing for 8-bit, 1-byte, encoding. Additional characters. Extended ASCII includes an expanded character set with additional symbols, accented characters, and special symbols. Usage. Text encoding. ASCII is widely used for encoding text in computing, communication protocols, and file formats. Compatibility. Many programming languages and applications use ASCII for representing characters in strings. Limitations. Language support. ASCII has limitations for languages with characters beyond the basic Latin alphabet. Unicode adoption. While ASCII is still prevalent, Unicode has become more widely adopted for supporting a broader range of characters from various languages. In summary, ASCII provides a standardized way to represent characters in computers, with each character assigned a unique numeric value for encoding and communication purposes. Representing numbers in binary. In computing, numbers are often represented using the binary system, which uses only 2 digits, 0 and 1. The process of converting a decimal, base 10, number into binary, base 2, involves breaking it down into powers of 2. Here's a step-by-step guide on how to represent numbers in binary. Understand the binary system. In binary, each digit is called a bit, and a group of 8 bits is a byte. The binary system follows a base 2 format, as opposed to the base 10 system used in everyday decimal numbers. Divide by powers of 2. Start from the rightmost digit of the decimal number and divide by 2 successively, keeping track of the remainders. The remainder at each step will be a binary digit, 0 or 1. Write in reverse order. After completing the division, write down the binary digits in reverse order to obtain the binary representation. Example: converting decimal to binary. Let's take the decimal number 13. 13 divided by 2 equals 6 with a remainder of 1. Rightmost bit. 6 divided by 2 equals 3 with a remainder of 0. 3 divided by 2 equals 1 with a remainder of 1. Leftmost bit. Reading the remainders in reverse order. 1, 0, 1. The binary representation of 13 is 1101. Binary fractional numbers. For decimal fractions, the process is similar but involves multiplying by 2 instead of dividing. The fractional binary digits are obtained by noting the whole number part during each step. Understanding how to convert decimal numbers to binary is fundamental for programming and working with computer systems, where binary is the primary representation of data and instructions. This process serves as the foundation for various operations within the digital realm. Grasp the concepts of bits, b, and bytes, b, essential units in computing. Understand the fundamental difference and how they contribute to data storage and processing. Bit, binary digit. A bit is the most basic unit of digital information and the fundamental building block of digital computing. It can represent one of 2 states, 0 or 1. The term bit is a contraction of binary digit. Byte. A byte is a higher-level unit of digital information, consisting of 8 bits. It is the basic addressable element in computer memory. Bytes are often used to represent a character in a computer's memory, with each character typically requiring 1 byte of storage. The term byte is derived from by 8, indicating the 8 bits that compose it. Further details. Bit. Smallest unit. A bit can exist in 2 states, representing the binary choices of 0 or 1. Binary system. The binary system relies on bits, with combinations of zeros and ones used to represent various data. Boolean logic. Bits are the foundation of Boolean logic, where 0 often represents false, and 1 represents true. Byte. Character representation. 1 byte typically represents 1 character in the ASCII encoding system. Memory addressing. Memory addresses are often specified in terms of bytes, indicating the smallest addressable unit. Data size. Bytes are used to measure the size of files, storage capacity, and data transfer rates. Common prefixes. Larger units, such as kilobytes, KB, megabytes, MB, gigabytes, GB, and terabytes, TB, are used to describe data sizes, each consisting of a specific number of bytes. Understanding bits and bytes is crucial in computer science and digital technology, as they form the foundation for encoding, storing, and transmitting information. The efficiency of data storage, memory management, and communication protocols often revolves around these fundamental units. Embark on the world of algorithms, the step-by-step procedures that solve problems and perform tasks. Learn about pseudocode and flowcharts, essential tools in designing and visualizing algorithms. Creating algorithms. Understanding pseudocode and flowcharts in computer science. Creating algorithms is a crucial step in solving problems and designing efficient solutions. Two common tools used to represent algorithms are pseudocode and flowcharts. Pseudocode. Definition. Pseudocode is a high-level description of an algorithm that combines elements of natural language and programming language syntax. It is an informal way to outline the logic of an algorithm before translating it into a specific programming language. Advantages. Readability. Pseudocode is easy to read and understand, making it a helpful tool for collaboration. Flexibility. It allows for a clear expression of logic without the strict syntax rules of a programming language. Planning. Pseudocode aids in planning and organizing thoughts before actual coding. Flowcharts. Definition. A flowchart is a visual representation of an algorithm using symbols to represent different steps, decisions, and processes. It provides a graphical way to understand the flow of control within an algorithm. Components. Oval, start, end, represents the beginning or end of a process. Rectangle, process, represents an operation or step in the algorithm. Diamond, decision, represents a decision point, typically involving a yes/no question. Arrow, flow direction, connects symbols to show the flow of control. Example flowchart for a simple algorithm. Creating algorithms with pseudocode and flowcharts. Planning. Begin by understanding the problem and breaking it down into smaller steps. Pseudocode. Write a step-by-step description of the algorithm in a syntax-agnostic manner. Flowchart. Visualize the algorithm using flowchart symbols to represent the logical flow. Refinement. Iterate and refine both the pseudocode and the flowchart as needed. Using pseudocode and flowcharts together provides a comprehensive approach to algorithm design, fostering clarity, and effective communication among developers. These tools serve as valuable aids in translating abstract ideas into actionable and implementable code. Explore the elements of a flow chart. Ovals for the start and end, parallelograms for input, output, rectangles for processes, diamonds for decisions, and more. Understand how these elements convey the logic of an algorithm. In the context of flowcharts, various elements are used to represent different aspects of a process or algorithm. Here's an explanation of common flowchart elements. Oval, start, end. Purpose. Represents the start or end of a process or algorithm. Description. Typically used at the beginning and end of a flowchart to indicate where the process begins or concludes. Rectangle, process, purpose. Represents a specific operation or action to be performed. Description. Used to detail the steps or actions involved in the process, such as calculations, assignments, or other tasks. Diamond, decision, purpose. Represents a decision point that results in alternative paths. Description. Typically includes a question or condition, leading to different outcomes based on a true or false answer. The flowchart follows different paths depending on the decision. Parallelogram, input, output, purpose. Represents input or output operations. Description. Used to indicate where data is input into the system or where results are output. Commonly used for interactions with the user or external data sources. Arrow, flow direction, purpose. Indicates the flow or direction of the process. Description. Connects the different elements in the flowchart, showing the sequence and direction of the process. Arrows guide the reader from one step to the next. Cylinder, data storage, purpose, represents data storage, such as databases or files. Description, indicates where data is stored or retrieved during the process. Often used to show interactions with external data sources. These flowchart elements, when combined and arranged appropriately, provide a visual representation of the logical flow and structure of a process or algorithm. Conclusion. As we conclude our journey, remember that programming languages are the keys to unlock the limitless possibilities of the digital world. Whether you're a beginner or an experienced coder, the beauty of programming lies in its ability to transform ideas into interactive realities. Happy coding, and may your programming adventures be both rewarding and enlightening.